Here we go. This is part one of the test review for the test on chemical bonds. The other video will show you the answers to the Lewis structures worksheet. This is the answer key for the questions and the one thermochemistry related problem. So first question, which of these is most likely to form an ionic compound? There are two ways to figure this out. One is you could look them up on the periodic table and pick the two elements that are the farthest apart, because those are most likely to have the greatest electronegativity difference. The other thing you could remember is that ionic compounds are typically formed when a metal bonds to a nonmetal, and the only case where that is true in this question is when magnesium and fluorine are bonded, because all these other ones are nonmetals and nonmetals. So the correct answer here is number 4. So we're going to do the Lewis dot formula, and in fact we're not even going to draw the formula, we're just going to work on the NaSl, and in this case just the NaS, because they don't even ask us about the L. So the need, so we've got, just to put the molecule down here, we've got a nitrogen with 3 hydrogens and a chlorine, which means we've got 3 hydrogens. So for need, 3 hydrogens means you need 6, right, 2 apiece. And then you've got nitrogen, which needs 8, and chlorine, which needs 8. So 6 and 8 and 8 is 22. Now they all say 22 for N, so that doesn't really help. Available. Well, we have 1 available from each of the hydrogens. We have 5 available from the nitrogen. And we have 7 available for the chlorine. And we would look that up on the periodic table if need be. So 1 plus 1 plus 1 plus 5 plus 8 would be 15. And that would be the trap answer, because we have to take into account, as it shows in the question, that this is a positive polyatomic ion. Positive means it has lost electrons, and in this case it has lost 1 electron. So the number goes from 15 down to 14. So A is 14. Now there's only one choice that has that, so right there we could stop. If you really wanted to, you could see that N minus A, which equals S, would be 8, but that's the only one with 14, so that's the correct answer. How many lone pairs of electrons exist on the central atom in ammonia? Well, to do this you'd need to either know it off the top of your head, which I don't think is likely, or you draw the Lewis structure. Okay, the Lewis structure, you've got N, which is going to be 8 plus 6 or 14. Got A, which is 8, S, which is 6, and L, which is 2. So right there, you could actually see that the lone pair number of electrons is 2, which means there's 1 pair. And there's 2 electrons that make 1 pair. You can draw it out if you really wanted to, and you'd see that there is, in fact, 1 lone pair, and it can only be on the central atom since everything else is a hydrogen. Never put dots on a hydrogen. Okay, which of the following is true about these ions and the one neutral atom? Well, if you look at these on the periodic table, hopefully it quickly becomes apparent that they are all essentially in a row, starting with selenium at number 34, then bromine, krypton, rubidium, strontium. And if you look at them in that way, and then remember that the fact that selenium gains 2 electrons, it goes from 34 to 36, which is the electron configuration of krypton. And then bromine gains 1 electron, go from 35 to 36. Rubidium loses 1 electron, goes from 37 to 36, and then strontium loses 2 to go from 38 to 36. They all have 36 electrons. They all have a noble gas configuration equal to krypton, including krypton obviously, which means that is called an isoelectronic series of species. They all have the same electron configuration. Which of these is the correct Lewis structure for oxygen, O2? And again, just remembering in this, in the quest, they use dots even to represent bonds. So 1 pair of dots in between atoms means a single bond, 2 pairs means a double bond, and 3 pairs means a triple. So you need to work out the NaSl, unless you happen to remember this, again, but So we have two atoms, they're both oxygen, no hydrogen, so that means we need 16. We have two oxygens. Each oxygen has 6 valence electrons, so there are 12 available, which means we need to share 4, and it means we're going to have 8 left over. So 4 shared electrons means 2 bonds, and then there would be 8 lone pair electrons, so 2 pairs on each. And since the quest uses dots to represent the bonds, the one with the double bond in the middle and then 2 pairs on either side would be that answer choice there. Also, some of these answers might be in a different order in the copy that you have. Sorry about that. So when it prints out multiple times, it scrambles the answer choices, but the answers are all the same. They just might be in a different order on the sheet you're looking at. And another Lewis structure for HCl. So H and Cl, just 2 atoms here. Well, you know H is going to be bonded once because that's all it can do. But just to go through the process here, N, we have a chlorine and a hydrogen, so we need 10. Chlorine has 7, hydrogen has 1, so that's 8, which means we're going to share 2 and have 6 left over. Since we have the 1 bond on hydrogen, we can put the 6 electrons around the chlorine, which gives it 8. And the 1 here that represents that is the H, the 2 dots in the middle, and then the 6 more dots around chlorine. Okay, so what does the N stand for in Lewis dot structures? That's the first sort of part of the question. And what would N be for oxygen? Well, you need to remember that N stands for needed, and for pretty much every element on the periodic table, the value for N is 8. And so, first of all, the only one with 8 is this choice, and some of the others have things that aren't needed. They're nearby or nested, which are not the right answer. So, answer choice needed electrons, and 8 would be the number for oxygen. What is the principle upon which Lewis dot structures are based? Well, they're based on the fact that most elements on the periodic table, and as it says, except for hydrogen, want 8 valence electrons in their outermost shell, and that makes them stable because it makes them like a noble gas. Hydrogen is an exception because it only wants 2. And that's really the basis of chemical bonds and, for the most part, chemistry in general. All atoms are trying to get 8 valence electrons, and they will do different things to get it, but that's what causes all different types of bonds and reactions to take place. What is the electronic geometry of ammonia? Well, we already saw a little bit earlier that the Lewis structure for ammonia, NH3, looks like this. So it has 1, 2, 3, 4 regions of electrons. So the steric number is 4. Anytime the steric number is 4, the electron geometry is tetrahedral. When in doubt, electron geometry is tetrahedral. That's going to be the answer most of the time. Now, if we were looking for the molecular geometry, it would be different because molecular geometry is affected by this lone pair, and then it would be trigonal pyramidal. But since we're looking at electronic, we can just count up the number and then know that 4 is always tetrahedral, and that's the most common by far. Which of these is false? Linear molecules certainly can be polar. Polar molecules have a net dipole moment. That's what makes them polar. They have one area of negative concentration and another area of positive concentration that are not canceled out. CCl4 is a polar molecule. Well, without even doing the NaSl, we'd see that CCl4 should have some structure like this, which means that it is symmetrical, right? It's got chlorine on all 4 sides, and 3-dimensionally it would be the 4 corners of the pyramid. So any molecule that is symmetrical cannot be polar, because even if there is a dipole moment, if there's a polar region, all of the dipole moments, which in this case would look something like this, are going to cancel each other out because they're all going in equal but opposite directions. So CCl4 cannot be a polar molecule. But just to look at the other choices, dipole moments can cancel, giving a net nonpolar molecule, which is what's happening in this case. And lone pairs do play a role in polarity. They actually play a very strong role because that's a sort of fixed point of negative charge, which gives most molecules that have lone pairs on the central atom are going to be polar. That's just another thing to look at. Which of the following is nonpolar? Well, I'm just going to roughly draw these out so you can see what they would look like without going through all the NaSl for each one. And again, remembering things from the last slides, that's H, not Br. CO2 looks like this. So what you're looking for is, for it to be nonpolar, it's got to be a molecule that is asymmetric. Sorry, for it to be nonpolar, it has to be symmetric. Asymmetric means it is polar. Okay, so these are all asymmetric in one way or another, either because of the shape or because this one has one bromine and everything else is a hydrogen, which makes it asymmetric. The one that is symmetric is the CO2. And it's linear, and it's got the same thing at both ends, and there are no lone pairs in the middle to bend it. That's what happens in these two molecules. If you just put the atoms down, you might think they were linear and therefore symmetric. But when you figure out that each of these has lone pairs on the center atom, that bends the shape, which then results in the shape being asymmetric and therefore polar. So the only one that's symmetrical is CO2. Which would be the most polar molecule? So we're kind of going in the opposite direction. First of all, you can cross off argon because that's in a molecule. And then looking at the other ones, we've got CH4. Okay, CF4 would be almost identical. You just replace the hydrogens with fluorines, so that's symmetrical. BF3 is kind of a weird one. You might think it's asymmetric, but boron is one of the atoms that can be an exception. It can be bonded to only 3 other atoms. We already saw that CO2 from the last question is symmetrical and therefore nonpolar, which leaves us with H2O, which has a bent shape with highly negative dipole moment here because of the 2 lone pair electrons and the fact that oxygen is strongly electronegative, so the dipole moments are going in this direction, and the fact that hydrogen gives up most of its electron, or gives it up most of the time, it becomes strongly positive on the other end. That makes water a highly polar molecule, which gives water some special properties that we'll actually talk about in the next chapter. The geometry and chemical bonds of water are best represented. Well, we just have looked at this a couple of times, but the overall shape of a water molecule is this bent molecule, which is most closely represented by this choice here. True or false, any molecule which contains polar bonds is a polar molecule. Well, stated this a couple of times. It doesn't matter. Just the only factor is not whether there are polar molecules, polar bonds or not. Polar bonds can create a polar molecule, but they do not create a polar molecule in cases where the polar bonds cancel each other out in terms of their polarity. So in oxygen bonded to carbon, the negative dipole moments are both going in opposite directions and equal because they're the same atom, so therefore they cancel each other out. And the same of something like carbon tetrafluorine, tetrafluoride. All these are polar bonds, but they are all moving in equal and opposite directions, so they all cancel each other out. So a polar bond does not a polar molecule make. What is the fact that determines the molecular shape? The shapes are determined by, as the name VSEPR says, valence shell electron pair repulsion. Okay, pairs of electrons are always going to repel each other, and therefore they will find positions within 3D space to give themselves the most room between them and the next electron pair, which causes them to take these fixed three-dimensional shapes. What do we do with VSEPR theory? We use it to predict the bonding pattern, and or the shape would be another way to say that. We don't predict electronegativity with that. We don't use VSEPR theory to predict, it's the three-dimensional structure, sorry. The three-dimensional structure is determined by VSEPR theory, which, as we saw in the last slide, is caused by the repulsion between pairs of electrons. The VSEPR theory is based on the minimization of repulsion among valence electron pairs. Okay, again, we saw this a couple questions ago. All of this is based on electron pairs repelling each other, and that's how they end up being in the shapes that they are, because they're trying to find the farthest distance away from one another. Which of these molecules is non-polar? You'd have to do all these out, but if you do the first one, CO2, or always just keep this in mind because we've seen it a few times now, CO2 is a non-polar molecule because it does have dipole moments aiming at the area of the oxygens, but because they're in equal and opposite directions, they cancel each other out. So CO2 is a non-polar compound. Which of the following would have the largest dipole moment? So here you're looking for the one that would have the greatest difference in electronegativity. Since H2 and F2 are the same atoms bonded together, it can't be either of those. So now we're looking at comparing HCl, HBr, and HI. So since they're all bonded to hydrogen, the one with the greatest difference in electronegativity is going to be caused by whichever one of these three halogens has the highest electronegativity. And since chlorine is the one of these that's closest to fluorine, it has the highest electronegativity. It's going to hog the electrons the most and therefore create the largest dipole moment. All right, so this last one, the thermochemistry problem, goes back to, again, the idea that a reaction, the change in enthalpy for a reaction can be calculated by breaking it down into steps and then adding all the steps together so that anything that's not in the reaction gets canceled out, and the energies of all those sub-reactions or steps gets combined, and the resulting net energy change is the energy change of the overall reaction. It's called a state function, so you can go through however many steps you need to. All that matters is what did you start with and what did you end up with. So you could, for the most part, you can almost just add all these things together. But I'm going to go through them in steps and kind of the logical progression of what's actually happening to go from solid magnesium and fluorine gas to solid magnesium fluoride. So the first thing that we have to do is we have to convert the magnesium to a gas. Okay, because the ionization energy that we're going to use in a minute is based on atoms in the gas state. So that is the sublimation of magnesium. So the enthalpy there is 150 kilojoules. Step 2, we've got to strip away the electrons, but we can't do that all at once in terms of looking at the process. So we're going to take magnesium gas and turn that into magnesium with a +1 charge, plus 1 electron. So we've now separated that electron from the magnesium, which is called the first ionization energy. So that's part 2. Has an energy of 735. These are positive values because it takes an input of energy. You have to add energy to get these things to happen. The next step is to turn that plus 1 into a plus 2. So we're going from magnesium plus 1 to magnesium 2 plus, and we've removed another electron. That energy is 1445 kilojoules. Okay, so now we've taken that neutral solid magnesium atom and turned it into an ion with a charge of plus 2 in the gas phase. The next step is separating the fluorine molecule into 2 separate fluorine atoms. And in order to do that, so this is step 3. In order to do that, we have to overcome the bond energy of F2, which is 154 kilojoules. Now that we have broken the bond, we have to turn fluorine into an ion so that it can combine with the magnesium. And in order to do that, we have to take the 2 fluorine atoms plus 2 electrons, and we end up with 2 fluorine ions. And that is electron affinity. How much energy is released when you gain an electron? And that's negative 328. But because we did it twice, it's 2 times negative 328. Okay, so we have taken the solid magnesium atom, turned it into a gaseous magnesium plus 2 ion. We've taken the gaseous fluorine molecule, separated it, and turned each of those atoms into a fluorine or fluoride ion. So now the last step is to combine the 2 ions that we've created. We've got the magnesium plus 2 plus the 2 fluoride, and we're going to combine those to create 1 magnesium fluoride ionic compound. And when we do that, we get back the lattice energy of that compound, which would be in reverse how much energy we'd have to put in to break apart this compound. That amount is negative 3916 kilojoules. So we've got all the steps, 1, 2, 3, 4, 5, 6. And if you want to just to look at this in terms of how do we get from all this mess to this reaction up here, well, here's what we've got. We've got magnesium gas on both sides. We've got a single magnesium ion on both sides. We've got a single magnesium plus 2 on both sides. We've got 2 fluoride atoms on both sides. We've got 2 fluoride ions on both sides. And we've got 2 electrons on this side, 2 electrons on that side. So what's left once we cancel out all that stuff is magnesium plus fluorine, solid magnesium plus fluorine gas on the left, and on the right is magnesium fluoride solid. So we're going to add all the energies together. Don't forget to multiply this one by 2. When you do that and add it all up, you get a change in enthalpy of negative 2088 kilojoules. That is the standard heat of formation, and that is per mole of magnesium fluoride. So there you go. The again, the Lewis structures problems are in the other video, which is also posted on this page, and that's it. So that'll be questions similar to all of those will be on the test coming up, and that's the end of this. Go watch the other video.